Hello, welcome to the continuation of Module 2 of Algorithmic Thinking. And in this session, we will continue with searching and sorting algorithm. So, searching and sorting algorithms are fundamental operation in computer science and are integral to many algorithms and data processing tasks. Understanding this algorithm is crucial for efficient data retrieval and organization. Okay, so types of searching and sorting algorithm. So in search algorithm or searching algorithm are used to find the position of an element in a data structure, be it array or list, right? Or any kind of data structure. Also, there are different common searching algorithms. The first one is a linear search. A linear search is a straightforward method to check each element in a list sequentially until the desired element is found or list ends. And time complexity for linear search is big O n, where n is the number of elements in the list. This means that we have linear time complexity, right? Use case, it is suitable for small or unsorted list. Why? Because as a list become bigger and bigger, also the time become larger and larger. So the time increase at the list increase because has a linear time and space complexity. Okay, so let's see these examples. So assume you have been given this Python function for linear search, right? So the linear search works in a different kind of data structure, and the way it works, it just traversing through the list to find whatever element or whatever item you need, right? So our function linear search take up an array, also take a target. So it need kind of data structure that you might need to find for a certain target. So a linear search, the way it works, it will loop over the list until it finds the exact target that you want. If it doesn't find that target, it will return -1. So if the target is found, then it will return the index of that target, right? So this is how it works. For I in range of lengths, right? So it will loop for our range of our list, right? So if you have 1, 2, 3, 4, 5, 6, we have 6 elements in our list. So it will loop 6 times, right? So it will traverse through this list to find the target, which is 70. So it will jump first, second, third, fourth time, it will see 70, and it will return the index of this element. So a linear search sequentially check each element in the list to find the target value. So in this example, the algorithm finds the target 7 at index 3. The time complexity of linear search is 0n, meaning the time it takes to complete the search grows linearly with the size of what? With the size of the list. Okay, we also have a binary search. So binary search is an efficient algorithm that repeatedly divides a sorted list in half, reducing the search area until a target element is found or the list is exhausted. So the time complexity is 0 log n, where n the number of elements in the list. This means that the size of our list might grow largely, but the time will grow slowly. So size of the list will grow largely, but the time will grow slowly. So that is its time complexity. So the use case is suitable for larger sorted list. Why? Because it grows slowly as the list grows. So take this example, right? In this example, we are using a binary search to find a specific target of our element, right? Yeah, so at linear search, it takes 2 parameters. It takes parameter of our list, which is array here, and it takes parameter for our target. Then the way binary search works, it divides our list into two halves, left and a right half, right? So if left and right are less than, what I can say is if left hand side is less than or equal to the right hand side, then we will loop over our list. How? Through dividing the middle. So this one is specific to find the middle item, dividing our list into two sorted proportions or two sorted portion of our list. So the first portion and the second portion. First portion is of our left hands and second portion is of our right hand side. So as you see here, we divide our list into twos. As you see, we have a mid list here, mid which is equal to left plus right divided by 2. So if array of mid is equal to the target, then return the mid item. So the first thing we do is to check the middle element in our list, right? Is to check the middle element in our list. See here we have 2, 3, 4, 7, and 9. The middle element in this list is 4, right? So if our target is 4, if our target is 4, we will just return 4. But see here, the target is 7. So that means that we need to find the 7 in our list. So because our mid item is not equal to the target, then we go to the else if, whereby in our else if we need to check if the middle item is less than the target, right? If the middle item is less than the target, then go search in left hand side. You see here the middle item is 4. We are finding 7. Means that 4 is less than 7, right? So if 4 is less than 7, that means that we need to search into the right hand side. So instead of going into the left hand side, then we will search to the into the right hand side. As you see here in the last right hand side, there is a 7. So it will find 7 and return it. Otherwise, it return -1. So this is how the list works. So as you see here, the output is 3, means that the output is index 3, 0, 1, 2, and 3. The index 3 is what the 7 found. So the algorithm check the middle element, and if it match the target, it return the index. If the target is small, it continues searching in the left hand half. If the larger, in the right half. So in this example, the function successfully find the target 7 at index 3. The time complexity of binary search is 0 log n, making it much faster than linear search for the larger list, because as the list grows rapidly or largely, our time for finding element or our time complexity grows slowly. So that's how binary search works. Okay, that is our searching algorithm. So let's see sorting algorithm. In sorting algorithms, arrange the element of list or array in a specific order, typically ascending or descending order, right? Okay, there are common type of what we call sorting algorithm, and the first one is bubble sort. So bubble sort is one among the sorting algorithm, and is a simple comparison-based algorithm that repeatedly step through the list, compare adjacent element, and swap them if they are in the wrong order. So the way bubble sort works, it just repeatedly steps through the list or traverse through the list or iterate through the list, compare the adjacent element, and swap them if they're in the wrong order. So this process is repeated until the list is sorted, right? So time complexity is big O quadratic, right? So in the worst and average case. So the use case is educational purpose or small data set, because we don't need it nightmare in larger list. So this is an example of a Python code exploring or demonstrating how bubble sort works, right? So as you see here, we have a function called a bubble sort. This function takes a list, right, as a parameter. Then we declare n, which will take the lengths of our list. So if we have 1, 2, 3, 5, 6, 7, 8, so the lengths of our list will be 8, right? Then it have an outer array. I mean, it's an outer loop, right? So these loops run n times, where n is the length of the list. So each iteration of this loop represents one full pass through the list to the move to the largest unsorted element to its correct position, right? One full pass. So if I'm starting with 64, I will compare 64 with all of these other adjacent elements. So I will compare with 34 first and check which one is larger. If 64 is larger than 34, then 34 going to the back, while 64 going to the right. So and so and so and so and so. So this outer loop will loop until it will loop by passing all the list, right? So we are saying that the loop runs n times, where n is the length of the list. So each iteration of this loop represents one full pass through the list to the move to the largest unsorted element to its correct position. We also have this inner list, right? For j in the range of zeros, n minus 1 minus n minus I minus 1. So the inner loop, this inner loop goes through the unsorted part of the list, right? So the range is 0 to n minus I minus 1 means that this one means that with each pass we check fewer elements. So at the largest one bubble up to the correct position, the value n minus I minus 1, make sure we don't check already sorted element at the end of the list, right? So because if I already check 64, I will continue to the right to check other element. I don't have to return back. So this one, make sure that I'm checking the fewer element at the largest one bubble up to their correct position, right? Then I will compare them and swapping. So I will check the adjacent element. If our element, our array of j and array of j1 here, if array of j is greater than array of j1, then I need to swap them, right? This will check if the current element is larger than the next one. So if it is larger than the next one, then we have to swap them. We have to swap them, meaning that the larger element move to the right, while the smallest element move to the left hand side. So for instance, I've been given this array of list 64, 34, 25, 12, 22, 11, and 20. So in our outer loop for I in range of n means that our I is what? Our I is starting from 0. So this 64 will check all of this adjacent array. So it first check with 34. So it compare 64 and 34. Because 64 is larger, then it moves to the right. 34 will move to the left. So it swap. Again, 64 with 25. 64 is large. Swap. Again, 64 with 12. 64 is large. Swap. Again, 64 with 22. 64 is large. Swap. 64 with 11. 64 is large. Swap. 64 with 90. 64 is not greater than 90, so we are not swapping this, right? So we have 34, 25, 12, 22, 11, 64, and 90 at the first outer iteration. Also 34 will compare everything here, so it will go in there and there and there and there and there. So the function bubble sort sort this list in ascending order. So the time complexity of bubble sort is 0 quadratic n, making it inefficient for the larger list compared to more advanced algorithms like quicksort or merge sort. Why? Because assume we have 10 elements in our list, right? So if we have 10 elements in our list, meaning that we have to iterate 100 times, right? So if we have 100 elements in the list, then we have to iterate 10,000 times. This means that as the list grows, the time complexity and space complexity grows quadratically, right? So that's how bubble sort works. Apart from bubble sort, we have this we call insertion sort algorithms. So insertion sort algorithm build the first final sorted array one time at a time by repeatedly picking the next item and inserting it to the correct position among the previously sorted items, right? So insertion sort works by gradually building a sorted portion of the list. It starts with the second element and insert it into its correct position in the sorted part. So it repeats this process for each subsequent, for each subsequent element. Think of how you would you would sort playing cards, right? In your hand, one by one. You have a playing cards in your hand. How could you sort them? You will usually use a insertion kind, right? So let's see how this insertion sort works. The time complexity is also 0n quadratic in the worst case. Use case is efficient for small or nearly sorted dataset. So see these examples. Okay. So first thing is our function called insertion sort here, which take array. So for I in range 1 means that we traverse or we iterate through 1 to the length of our array. A length of our array is 1, 2, 3, 4, 5. So the length of our array is 5. So it will iterate 5 times, right? Then after iterating 5 times, then what it do? Then we have a key which is equal to array of our index. So key is the element at index I that we are trying to insert into the correct position in our sorted part of the list. For instance, we have I is equal to 1, then the key of array 1 will be equals to 11 because we are not starting from 0. We are starting from where? We are starting from 1. Index 1 is what? Index 1 is 11. So at the first time our key is 11, right? So the while loop check if the element at index j is greater than the key. If it is, then we move the element at j one position to the right. This one while loop, this one. It check if the element at index j is greater than the key element. If it is, then we move this element at j one position to the right, as array j plus 1 is equal to array of our j. We keep moving element to the right until we find the correct position for the key. So when the condition key is less than array of j, which means that false, then we stop and the key is inserted into its correct position. So that's how our insertion sort algorithm works. So assume we start with 11, right? Because 11 is our first index, 11. We don't start with 12, we start with 11. So we compare 11 with 12. 11 is smaller. So if 11 is smaller, then we move 12 to the right. We move 12 to the right. This one, say we move 12 to the right. Then we insert 11 into the correct spot. It means that we insert 11 in the position where our 12 was before. We also go to the step 2. Our step 2, I is equal to 2. I is equal to 2 means we are looking at I is equal to 2. Key is what? Key 13. 0, 1, 2, key is 13. So we check. 13 was 12. We are not checking zeros. 13 with 12. Remember, where we have 11 here now, we have 12. So checking 13 was 12. Which one is larger? 13 is larger. So we need to move, we don't need to move 12 because it is in the correct position. So we go again until we have our sorted array, right? So this function insertion sort the list in ascending order. The algorithm is efficient for small dataset or nearly sorted dataset with a time complexity of 0 quadratic n in the worst case scenario, right? Yes, so we have a merge sort. Merge sort is divide and conquer algorithm that divides this list into smaller sublists, sort them, and then merge the sorted sublist to produce the final sorted list. So we divide our list into 2. After dividing our list, then we sort those lists half by half, half by half, half by half, until we have a correct sorted portions of the list. At the end, we merge them, all these sorted sublists, to produce the final sorted list. So you're saying that a merge sort is a divide and conquer sorting algorithm. You divide the list into two halves recursively, sort each half, and then merge the two sorted halves to produce a final sorted list. It is known for its efficiency with time complexity of 0n log n in all cases, which is better than bubble sort and insertion sort for the larger list. So in worst case scenario, merge list will also shine, right? Yeah. So it's suitable for larger dataset. So assume we have this one, as I said before, that the merge sort algorithm will divide our list into two. We have left, right, and mid. We will again merge. After merge, we will call merge. This merge, what it does, merge it check our left hand side and our right hand side of the our list. So it will be merging, it will be dividing our list until we sort all of them. So this with this while loop here, this while loop here will compare the element from the left and right at the current index of I and j. The smaller element will be added to the result and the corresponding index I and j, or incremented, right? So let's see quick sort algorithm. A divide and conquer algorithm that works by selecting a pivot element and partitioning the array around the pivot. The element is smaller than the pivot, go to the one side, and the element larger than the pivot, go to the other hand side. The process is then repeated recursively for each portion. Time complexity is this one in all case scenario. Sorting larger data set, efficient average case sorting, that's a use case, right? So see this example, attempt it by yourself. So you have been given an activity that you are required to implement 5 different sorting algorithms to sort this kind of array in ascending order. So question to answer is, write a Python function for each of the above sorting algorithms. Compare and discuss the time complexity and the space complexity of each sorting algorithm. Then decide which algorithm performs best when the array is already sorted. So take your time, take your moment, pause the video, and perform the activity. Okay, so this is a simple activity feedback which doesn't cover the first one. So the question 2, which we compare and discuss the time complexity and space complexity of each sorting algorithm, right? So the merge sort and the quick sort both have an average case time complexity of 0n log n, making them the most efficient for typical inputs, right? And question 3, insertion sort perform best when the array is already sorted with time complexity of 0n. So it only compares adjacent element, does not require any swap. So it's highly efficient for nearly sorted array insertion sort. Remember, in worst case scenario, you might not need to use insertion sort. Okay, so this marks the end of our module 2. In the next module, we will learn about project-based learning.